continuación doy la palabra a la doctora Perla Olivia Rodríguez, quien nos presentará la primera conferencia magistral de la doctora Nadja Wallaszkovits de la Academia de Ciencias de Austria. Doctora Perla, a usted la palabra para presentar la primera ponencia magistral.
Muchas gracias, doctor Mateo. Para mí es un honor contar con Nadja. Nadja Wallaszkovits es una de las profesionales e investigadoras más reconocidas en el mundo de los archivos sonoros y audiovisuales. Es una referencia a nivel internacional y ella es una pieza clave en la Asociación Internacional de Archivos Sonoros y Audiovisuales. Ella ha trabajado en la Phonogram Archive de Austria, que es la primera fonoteca del mundo. Y ella ha trabajado mucho en proyectos que tienen que ver con la digitalización de archivos sonoros y audiovisuales. Y quisiera comentarles que actualmente es profesora invitada de la Universidad de Viena y de las Universidades de Ciencias Aplicadas de Berlín y Berna. Invitamos a Nadja en este congreso porque es precisamente una de las investigadoras que está trabajando propuestas, soluciones para intentar aminorar el impacto que tiene el uso de la tecnología y que provoca, es uno de los factores del cambio climático. Nadja, thank you for your participation. Welcome. If you want to share your slide, will be welcome, and you can start to participate in the Congress.
Okay, thank you very much, Perla, for this very nice introduction. I feel very much honored to be invited to give a speech at this wonderful event, at this wonderful symposium. Many thanks for the invitation. And yes, I would like to talk to you about recent developments in energy saving and audiovisual archiving. And I will show you a route to how analog archiving can go digital in a very intelligent and clever way. But before we come to this point, we start with some basic problems which all of us are facing currently. So global warming and global climate change is a major problem for all of us, for all human beings, the whole environment, for our life on the planet. So the global climate change has also effects on archival materials, which we eventually do not consider immediately. And this is, for example, that the climate change is raising average temperatures and also the dew points, which certainly affects the storage and long-time preservation of audiovisual materials. It is increasing the likelihood of catastrophic weather events like floods, droughts, fires, energy supply disruptions, and many more. And we just recently had a severe catastrophic scenario in Germany where a flood has affected a large region and where many archival holdings and pieces of art had suffered from this effect of the global climate change. Therefore, no institution can afford to ignore its own role in sustaining Earth's resources, and audiovisual archives can contribute to a better environmental behavior if they just try to implement a few basic factors. So the global environment means that analog as well as digital audiovisual archives are severely contributing to greenhouse gas emissions. Analog, due to the climatization and climate control, which is very energy consuming, especially if you try to keep the levels very stable, and if you have to keep a cold temperature for example, for the long time storage of film materials, which need to be frozen or need to be cooled very much. But also they can also digital audiovisual archives create a lot of energy if you think of all the servers and all the cooling for the servers, which you have to keep upright all the day during the whole year. This is a lot of energy consumption, and we can try to improve this, the CO2 footprint of all this by reducing our energy consumption or by changing to different technologies. So especially analog audiovisual archives can also cause direct toxic endangerment to people. And this is, for example, the case if you think of the outgassing of audiovisual materials, especially of films, which is not very healthy. There are chemicals involved that are not very healthy, but especially in the case of a catastrophe like a fire, if audiovisual materials are burning, they cause a lot of toxic, highly toxic gases, which will then pollute our environment, certainly in a very bad way. So the general problems are also, so how to try to avoid such scenarios, how to optimize storage situations. So one of the biggest problems is that buildings are the largest consumers of energy. So buildings, especially new buildings with less isolation, cheaper built, thinner walls, they can cause a lot of energy lacks. And traditional materials, to the contrary, are generally very durable. The continued maintenance of historic buildings and features relies on local craftsmen rather than on the replacement of parts. And these structures generally make up the heart of our towns and cities anyway. And for decades, preservation and the knowledge about how to build a building have been transferred to the next generation, and the old buildings with their thick walls, they basically bring a good isolation from the start of, from the very beginning of their existence. So the continued maintenance of historic buildings and features is much more energy saving than building a new building with a different concept, with high energy consumption, just somewhere on the green meadow, which is unfortunately very often the case, especially also here in Europe, but I think also in other parts of the world. So buildings are largest consumers of energy, and having a good idea of using a historic building in an intelligent way can contribute very much on the long term to energy saving. Yes, there is a commonly quoted phrase which says, the greenest building is the one that is already built. And this expresses the relationship between preservation and sustainability. The repair and retrofitting of existing and historic buildings is considered by many to be the ultimate recycling project. And focusing on historic buildings has added benefits for the larger community. So using a historic building is very good, especially if you can place the archive to the inner part of the building. Let's have a look at this slide. Here you can see a model of a tropical AV archiving building, audiovisual archive building. And you can see in this slide, in this drawing, that the storage area is somewhere in the middle of the building, and the building has thick walls around the whole, thick isolation walls around the whole complex of the storage area. And all the working and rooms and offices and laboratories are positioned somewhere around, but the storage area is not in the basement, and it's also not at the roof of the building. And this has advantages because the basement is always problematic concerning water. Many storage areas have been put into the basement, and several of them have been flooded so far, causing disasters of catastrophic scenarios, which is really the worst thing you can have in an archive, a flood. So putting the storage area somewhere in the middle of a well-isolated historic building with thick walls is a very good strategy and energy saving strategy, and also a moderate concept for a tropical archive. For example, in this model, you can see that the walls there have an outer insulation, and this allows air fluctuation. So the cool air, which is sinking down to earth, will warm up during the day and then evaporate over the roof. And this keeps a steady air fluctuation around the center of this building, and this is the storage area, and therefore keeps the inner part with the audiovisual materials basically in a better climatic condition as if you have another concept of building. So an additional or alternative strategy is to apply new technologies on historic properties. For example, one possibility is to apply and use solar panels. We all know that solar panels are now the actual technology which will hopefully help to save our world and hopefully improve our CO2 footprint. But as we all know, solar panels also have their disadvantages concerning energy consumption on production and concerning the materials that are used on the production process. Nevertheless, if they have once been produced, they are very, very effective, and adding solar panels to historic properties can have a significant impact on the character and visual qualities that cover properties' cultural significance. So this is very important to take into consideration, that solar panels have to be mounted in a way that the historic property will have the same visual impact than without his solar panels. The installations should not become prominent new elements that detract from the character defining features of a building or of a landscape. So this technology certainly has to be considered, and if applied, has to consider also the historical and the landscape aspects of the building and the environmental aspects of the building and its surrounding. Another technology, which is also very recent technology and very effective, is the use of wind turbines. So since ever, in many regions worldwide, windmills have often been characteristic and traditional features of the landscape. And now, as the demand for alternative energy sources grows, the introduction of modern wind turbines in historic settings will also likely become more common. And planning for the introduction of such wind turbines means also that the protection of the historic setting and the context of the property has to be considered as well. And also including the degree of open space and building density, also the necessary distances to other buildings, and so on and so forth. So as always with new additions, the massing, size, scale, architectural features of new constructions on the site of a historic building must be compatible with those of the historic building and with the protection of the historic building as well. Nevertheless, wind turbines can be very effective and can help to save energy very much. So another technology which I only mention and do not go too far into is the idea of having green roofs or green walls. Basically, this is a very good idea, but I think it is not the best solution if you want to use it with archival buildings, because as we all know, green plants attract any kind of insects, pests, and other animals, and also fungus, the possibility of fungus growth, of pollution coming from the materials. And additionally, green roofs need water. And if you have water on the roof of an archival building, which is used to water the plants or to water the wall, you have the risk of wetting the walls or wetting the roof and then contaminating your archival materials at a certain point. And this should be avoided whenever possible. So for environmental planning, please keep in mind that technology is extremely helpful. Have a look for the most actual and most cost-effective technologies in the long term. So purchase clean energy wherever it is possible, and do not rely on coal-generated or on other environmentally not beneficial energy forms. Also, for a digital archive especially, but also for an analog archive, purchase hardware that is energy efficient. Have a look at the energy consumption and consider this in your calculation for the next decades, because as we all know, such equipment has to overcome long periods of time and therefore will consume a lot of energy. And therefore, this is an important point. If you recycle something by reuse, then you should vendors who don't ship overseas try to keep your purchases regional and local, even if it might be cheaper if it is shipped from somewhere else in the world. Try to avoid this. Try to save this energy for our environment. And something that is also not considered to be relevant, but it is in fact, is that, for example, all data tapes and hard drives you have to recycle because they are obsolete due to technology changes should be recycled with vendors who strip out parts and recycle the components, because this is also contributing to an energy-saving environmental behavior. So, if possible, use less energy. The best energy saving is made if you are just not using energy. Using less electricity helps the environment, plus saves your money. Store large and infrequently accessed files offline on data tapes. So try to use your try to use your excess copies, have them in a smaller data reduced size on a small part of your server, which is all in all less energy consumption. Then if you store all your large, huge files on spinning hard disks, because spinning hard disks take 26 times more energy than storing and infrequently accessing data tapes. So it's much less energy consumption to use a data tape from time to time than to keep spinning hard disks running all the time. And very important, keep storage conditions as stable as possible. It is very energy consuming if you start to turn off and on your climatic if you always have large changes, because then your climate control has to work much harder and much more and has to start from a very high temperature, leveling down, cooling down, then you power it off. You think you save a lot of money, but all in all, keeping the storage conditions as stable as possible is a very, very good strategy and helps to save all this energy. Recently, audiovisual preservation knowledge has fortunately evolved, and we now have a much better understanding of the equilibration rates and the impact of various enclosures on storage. So there is an emphasis on environmental consistency and now defined as a risk avoidance. And generally, the strategy is use cooler temperatures where possible, but the relative humidity might be allowed to vary generally between 30 to 50%, depending on your region. And always when choosing your climate conditions in your storage area, consider sustainability, consider values that you can keep over the long time for a very stable way. This is the most energy saving and also best possible storage condition for your media. Audiovisual media suffer most if they have to be under climate changes, under quick climate changes, from high temperature to low temperature during night, and during day again you cool down, you do not get rid of humidity, you do not dehumidify, and then humidity rises, then you think, okay, now I have to start dehumidifying and so on. So this is all not good. Climate changes and changes in humidity affect the stability and the longevity of audiovisual materials. And they trigger chemical reactions, and they trigger as well fungus and pest. So meanwhile, also various standards and guidelines have started to acknowledge this new knowledge, audiovisual preservation knowledge, like the standards here cited. And the new goal is an optimal preservation environment. The optimal preservation environment is the one that achieves the best possible preservation of collections at the least possible consumption of energy, and which is sustainable over time. This should be a major thinking of an archive to protect both the audiovisual media as well as our environment. Now, in the second part of my presentation, I would like to focus on a project where I'm involved in on behalf of the Phonogrammarchiv of the Austrian Academy of Sciences in Vienna. And this is the project Nemousine. It is about an innovative and energy-saving package concept for audiovisual media. This is one second. So Nemousine is a European Union founded project for the development of innovative packaging solutions for the storage and conservation of audiovisual media and cultural heritage artifacts with a focus of materials based on cellulose derivatives, such as cellulose acetate and cellulose nitrate. The objective of this project is to improve traditional storage solutions by developing an innovative packaging with the main goal of energy saving and extending the lifetime of the media. In contrast to conventional tape boxes and film cans, the packages will be equipped with the latest sensor technology based on multi-nano sensors for different gases. Then it will be also equipped with adsorbers for decomposition products, such as, for example, acetic acid or nitric oxides, and a control software platform that simulates the degradation process and then will predict accurate protective treatments. So you can say that with this new box, analog archiving will become digital in a way. I will show you some examples. So the problem is that more than 75 years of visual and audio memories are in serious danger to be lost due to the natural instability of cellulose acetate. The worldwide estimation of such holdings is around 18 million of film reels at least on cellulose acetate, whereof at least 5% are in a critical stage or showing severe signs of Vinegar Syndrome, as you can see here in the pictures. So the main preservation issues in audiovisual archives are chemical deterioration and damage of the media. Insufficient prevention of chemical deterioration due to bad storage conditions. For example, as we have discussed before, the lack of cold or sub-zero storage for film holdings, which is a big problem, but is also a big energy consumption problem. The chemical deterioration causes mechanical damage, for example, to the perforations or the edges of a tape, and also biological damages like fungus growth. We all know the main preservation problem of cellulose acetate, the so-called Vinegar Syndrome. If you open a box and it smells like vinegar on your salad, you know that you have a problem. It's a hydrolytic deesterification of the cellulose acetate that produces acetic acid by itself and therefore is autocatalytic. That means that one box can affect the next film box. And autocatalytic means that the more acidity is produced, the more the process is triggered and the faster the deterioration is going on. The second reaction is chain scission of the cellulose acetate polymer, which is most dreaded because it can lead to the complete and total material breakdown. I am showing my famous horror picture show here. You can see highly deteriorated and highly shrunken due to the loss of plasticizer, highly shrunken materials which are unplayable in this state and have to be restored with a very, very time-consuming and also expensive process. Here you can see some examples of cellulose acetate magnetic tape. Here you can see the famous or well-known spoking effect, like the spokes of a wheel. You can see this deterioration. And this is an example of material at the end the total breakdown of a magnetic layer with the base of cellulose acetate. So it simply breaks completely down, and there's no help anymore to this tape. And there is also no help to this disc. This is a lacquer disc which suffers from a nitrocellulose lacquer disc, which suffers from delamination caused by the Vinegar syndrome and by plasticizer loss and by bad storage conditions, in combination with fungus, mold, as you can see here on this brownish part of the disc. This disc is lost as well. And the same is valid for this disc. Also, this disc is lost. Fungus is also a well-known problem in archives, and also pest is problematic. Here you can see, for example, the effect of termites. Termites like to eat the boxes and the paper around the media, and this is the secretion of their digestion, sticking on this disc and contaminating this lacquer disc in a very, very bad way. So up to now, it is very time consuming to do a condition assessment, for example, in a film archive for cellulose acetate. The first visual and sensitive check is to smell. If it's vinegar, you know you have a problem. But then also by inspecting visible deterioration systems. And one helping aid you have is the use of acid detection strips, so-called AD strips, which usually have only between 5 or 7 values. That means that it is a estimation around the thumb, how high the level of deterioration of your item in the box is in reality. You can just estimate by reading the outgassing acidity in the on the AD strip. For nitrate, there is a visual assessment most common, but it's very challenging in practice, and chemical tests are available, but they are expensive and usually can only be performed in a special laboratory, and therefore are not undertaken in practice very often. So here you can see the work with film material, the AD detection strips. Each package has to be opened, the strip has to be positioned, the package has to be closed, has to be monitored again after 24 hours, and then you know the amount of acidity outgassing from a film, but you can never be sure because this measurement is depending on humidity and on temperature. The AD strip paper is sensitive to humidity and to temperature, and there is a lot of failure, and the accuracy of this method is not too high, to be honest. So in this way, Nemousine tries to monitor systematically the chemical condition of the cultural objects by using sensors inside the box, or at least attached to the box, and by developing a prediction model for the deterioration behavior, so that you can have a prediction about the sensor data, which will help you to go ahead with necessary measures. So these packages, the Nemousine package, will be a so-called smart package, a package that is very tight, so it has a high oxygen barrier, and you can have active functionality by using additives such as acid scavengers, acid adsorbers, which are based on functionalized metal organic framework and which are therefore very, very effective and specifically catch the acidities and not other components like, for example, plasticizers. They react only to acidity and not taking out plasticizers from the material. So I will go a little more ahead. So the concept is that you have a package design with a tight box, and you can add a foam which keeps these adsorbers to the box, and the box is connected to the sensor, and the sensor is connected to your prediction model and to your software, which you can eventually in future have on your mobile phone, and then you can check your boxes in the mobile. Then you can change your boxes from the software. So the system will be modular. This means that you can have only the box or a box with the adsorbers and with also protective layers against fungus, which is then a curative box. So this is the Nemousine consortium. It consists of 16 international project partners which work together on this project and which are working on the research route on different work packages to bring together this product idea. So I would like to focus on two very interesting work package parts. The one is the absorbers, the acetic acid absorbers using fractionalized MOFs. So why is this so intelligent and clever in comparison to existing solutions? A MOF, a metal organic framework, is a microporous structure that's composed of organic and inorganic components. And MOFs have shown a significantly better performance in capturing highly volatile acetic acid in the presence of moisture than other conventional adsorbers in conditions normally found in museums and archives. So here you can see a schematic picture of a metal organic framework. This is a very, very fine structure, and the metal ions form nodes that bind the arms of the organic linkers. And this is a hollow structure, and therefore MOFs have an extraordinarily large internal surface area. And this means, for example, that if you take a teaspoon full of such MOFs, you have a surface area of more than 7,000 square meters per gram. This means that you can cover a football stadium, a football area with just a spoonful of this metal organic framework material. And this means in practice that these materials are extremely effective for capturing acetic acid because their surface is shaped in a way that they can really attract a lot or catch a lot of acidity from your from the box where your audiovisual item is stored. So these are very effective acid scavengers. Here you can see the production model reactor where these new materials are produced. And as I have already outlined, these MOFs can be shaped to individual needs. This means that they can catch chemicals as adsorbers, but they can also release other chemicals like for example, fungicides. But so far, there are still some challenges in the production, like a cost-effective and also a green production way, like the synthesis in green solvents, and the interlinking and the recycling of the materials for the use in archives. And this is developed in the Nemousine project. Here you can see some yeah. Oops, I'm sorry. This is here you can see the structure of these different materials where the morphs can be linked to, and this nanofibrous materials will then be put into your audiovisual package and help you to reduce acidity content in the package, and therefore helps you to save energy in the cooling process of your archive storage vault. And the second work package, and the last one I want to introduce, is the development of the sensors, which are nano sensors to monitor the main gases involved in the deterioration. This is acetic acid and nitric oxide. And the sensors are based on nanotechnology, and they are they will be used for the measuring of outgassing chemicals. So the first question in our project was, which outgassing chemicals are relevant? Is it only acetic acid, for example, with cellulose acetate, or are there other relevant gases? So the sensor can also be used for the identification of nitrate film, which then is also a very, very good thing. Because to date, there is no 100% method to identify nitrate. So what we did in our project is that we measured existing deteriorating films by the help of the so-called solid phase microextraction. This is a very tiny glass tube that is positioned in the box that will, as is a fiber, and this fiber takes on the outgassing from the film and then is heated in the gas chromatograph and analyzed. And then you can find out which substances are outgassing from the film. Here you can see such a fiber. Here you see the glass part positioned in the package. And here you can see a spectrum as received from the analysis. And very interesting in this picture is here in the first in this region, you see acetic acid, but you see a number of adjacent very high peaks, which means that the film is not only outgassing a very high amount of acetic acid, but also other chemicals, which could, especially in this region, influence the measurement of the sensor, and which will definitely also influence the pores, for example, of as an AD strip. And therefore, the sensor has been optimized to exclude other chemicals than the relevant ones. And this gives the system a very, very high accuracy. Here is a measuring system and a measuring setup system. And here you can see the prototype, the actual prototype of this sensor array, which still has to be minimized and has to be developed to a smaller size, but nevertheless, as it is very effective, it is a first step, it is a first prototype. Here you can also see the control platform for the software, which is attached to the sensor. You have the sensor, some details about the film, And then you certainly have the measuring values of the film and some conditions, and the model will help you to predict and to tell you, for example, when to exchange the acid scavenger, then when is the acid scavenger saturated, and when to exchange it, and also if the acidity is outgassing so in a such high amount that you always have to exchange the acid scavenger, then it will recommend to copy or to proceed with digitization of the item. This is a very first model where you can see that the sensor is not inside the box, but attached in a very tight way, so that all servicing of the sensor and of the batteries, etc., is kept outside of the box. So the box does not have to be opened, despite you want to change the acid scavenger. All in all, I think I will skip a few of my slides. And I would like to come to an end now very soon, and to a summary. So the system can also be used not only for individual films, but also for the monitoring of the climate, acidity, and nitric oxide, and certainly temperature and humidity in a whole storage area, for example, on a shelf or on a part of your storage room. So to finalize to summarize my presentation, I would like to focus once again on this new idea of having a modular intelligent packaging solution, which certainly will not replace current storage systems, but will significantly improve the storage systems, which will help to monitor the collection by the help of sensor technology. And this is a great improvement because you don't have to once packed in such a package, you don't have to open the box. You can just read remotely this outgassing chemicals from your sensors, and you have a good overview of your collection and about measures and about use of climatization and use of energy on this part of the collection. The system will also help to frequently inspect the collection between periodical inspection dates. The software in the end will alert the archivist of the degradation immediately when it starts, and this will allow immediate decision making, and hopefully there will not be forgotten tapes and surprises on the shelves. So analog physical object-based archiving will become digital once these packages are in general used, and this most probably is one of the last chances we had to do basic research on these materials within a consortium of 15 high-ranking European project partners. So all in all, Nemousine project will help to preserve AV materials in a sustainable, intelligent, and energy-saving way. We are trying to implement and consider recycling strategies best possible, and we will try to help to reduce necessary climate control to a minimum of energy consumption, and producing the Nemousine packages using green technologies. The only disadvantage I have to say is that the project is still not yet at the end. The package is still not yet available for being bought. This is the disadvantage. But now I would like to thank you very much for your attention, and I'm looking forward to your questions. Thank you.
Thank you so much, Nadja. This conference was wonderful. Gracias, Nadja, por esta maravillosa conferencia que nos ha permitido conocer soluciones de vanguardia que son resultado de la investigación científica. Yo quiero recuperar una frase que Nadja compartió. El proyecto que ella nos presentó busca proteger a los archivos, pero también al medio ambiente. Y esta frase es muy importante porque denota la orientación y el esfuerzo que los científicos están en este momento impulsando precisamente para reducir el impacto que la tecnología de la preservación implica en el medio ambiente. Quiero agradecer de nuevo a Nadja porque nos ha permitido precisamente traer a América Latina desde la región andina un problema contemporáneo. Si bien es cierto, aún tenemos rezagos en la preservación, en la digitalización y en la preservación digital de nuestras colecciones, tenemos que pensar también en cómo salvaguardar el medio ambiente y tratar de proteger nuestro patrimonio sonoro y audiovisual. Nadja introdujo precisamente una serie de conceptos que nos acercan al cambio climático y al uso de diferentes tecnologías. Se refirió a los desechos tecnológicos y precisamente a la necesidad de utilizar menos tecnologías. Nos invitó a considerar la estabilidad, mantener condiciones estables en nuestros archivos, pero sobre todo nos presentó tecnologías de vanguardia que se están desarrollando, aún no se concluyen, pero están en un muy buen puerto. Me gustaría muchísimo agradecer a Nadja por ser la conferencista magistral. Thank you so much again, Nadja, because with your keynote speech, we opened the works in the International Congress, and we are going to start the discussion about the climatic change and the digital sound and audiovisual archives. Thank you so much.
Thank you very much, and thanks for all the nice comments I have seen popping up. Thank you very much. I feel very much honored about your nice comment. Thanks.
Thank you, Nadja. Y a nuestros participantes quiero decirles que con esta maravillosa conferencia iniciamos el Congreso Internacional de Archivos Digitales. Thank you so much again, Nadja. See you later.
Thank you. Bye bye. Thank you very much. It was my pleasure. Bye.